Okay, thank you. Thank you, Gabriel. Thank you for the nice invitation to speak in this online gathering. So I'm going to speak about like a whole course of work we've been doing in the last 5 years or so, since COVID actually as well. Um, at Humboldt University with a great team of collaborators and students, which I want to show you on the next slide. So these are in particular the students Benjamin, Matthias, Jitze, and Katrin, as well as the postdocs Gustav, Kais, Johann, and Gustav Morel used to be a postdoc with us. He's now lecturer at Queen Mary. And then we also added two mathematical physicists on the team, Christoph Neger, who's now at MPI Potsdam, and Albrecht Klemm from Bonn, who just recently moved to Sheffield. And it was really a big team effort, and I'm happy to show you the results of our work here. So what's the topic? The topic is maybe as old as theoretical physics as a science itself. Namely, imagine you empty the universe and you just put two masses in and let them interact gravitationally. They, of course, are on initial trajectories, and depending on the initial parameters, they might just scatter off each other. And when they do, due to their acceleration, so you have accelerated masses, they generate gravitational waves. And the task and sort of, the theme of our work is to make precise predictions for the outcome of these scattering events in classical GR. So classical gravity, we have two initial black holes or neutron stars, which fly past each other, get deflected, and what we want to compute are observables like the final state. So in this case, it would be the scattering angle and also the wave profile at infinity, or questions of how much energy is radiated away by gravitational waves in such a scattering process. This is not only of theoretical interest, but it is also very relevant for gravitational wave experiments, which of course have opened up a new era in like in astrophysics and beyond. Famously was the first detection of gravitational waves in 2015 by LIGO, and since then more than 200 events of binary interactions, in particular, not the scattering situation that I've been showing you in this little visualization, but the bound state and the merger of two black holes or neutron stars has been observed by the LIGO, Virgo, and Kagra observatories. But in particular, there are plans to build new observatories in the next decade, which will increase the sensitivity dramatically up to a factor of 100, or also in the case of LISA, which is space-based its instrument, will open up the window to lower frequencies. And importantly, this increase in precision for the measurements, as well as the sensitivity to low frequencies, necessitates a dramatic extension of the existing theoretical wave predictions beyond the state of the art. And that's where sort of our methods based in quantum field theory could be of help, or are of help. This is, an interesting topic, not only from an astrophysics perspective, but also there are very fundamental questions which touch most of us more maybe, but are involved and might be advanced through these observations, like testing Einstein's theory in new domains. There possibly even signals beyond the standard model, and then more astrophysical questions like black hole formation. How do black holes form? What's their population in the universe? Or also neutron star properties, which are particularly interesting for nuclear physics, of course. So it's a very broad arena of physics questions that you can address. But the basic is that you understand the standard model of these processes very well, and the standard model here is, of course, classical GR. So what we're interested in is the gravitational two-body problem, the fully relativistic gravitational two-body problem. And of course, the main players in this game are the objects of highest mass densities in our universe, namely black holes or neutron stars. Famously, black holes are very unique objects. They're uncharged. They're just parameterized by their masses and their spins. Neutron stars have more degrees of freedom, and understanding their properties is also something that is a goal of these gravitational wave observations. So the situation that one has, and these are the detections that LIGO and Virgo and Kagra perform, is that you have a system of two of these compact objects which encircle each other for billions of years, constantly emitting gravitational waves in this in-spiral phase, in this blue phase here. And due to the loss of energy, they come closer and closer. Their frequency increase until they finally merge into one object and then sort of ring down to a static state, again, a black hole or potentially a neutron star as a final state. Now, of course, the merger process and also this ring down are things which happen very fast, whereas this in-spiral phase is a very long phase, and this is also because the frequency goes down. It's something that with LISA one can observe for a long time. Also, this in-spiral phase is a phase where perturbative, so weak gravitational field approximations are good. And that's also the domain where we will be interested in. So perturbation theory, an expansion about a flat Minkowski vacuum for the metric field in powers of Newton's constant is what we are going to be interested in. Because this is exactly the domain essentially that people have been studying, or we have been studying in perturbative quantum gravity for a long time. And these techniques that were developed there can now be fruitfully imported to this classical physics problem. Of course, if you want to understand the merger, a numerical relativity is very good because it can, it does not need to assume it works very well for strong gravity, but it is very costly for these simulations to go to this into this in spiral regime for a long time, and generally these simulations are very time consuming. And for the data analysis of these processes, one needs gigantic tables or templates of waveforms in order to sort of identify the signal. And this is in order to fill these templates with varying parameters, analytical results are needed. And that's why these works that we have been doing are also relevant for the future detectors. So before I get into the details of our contributions, let me give you a brief overview of the three different perturbative schemes that are on the market and that are being pursued in order to describe or to quantify this in spiral phase. So the most well-studied one is the post-Newtonian approximation. This is essentially an approximation where we assume a large separation between these two objects. What does large mean? So the distance is large with respect to the intrinsic sizes, so typically the Schwarzschild radii of the two objects. And in that domain, the gravitational field is still weak, but not only does one do a weak field expansion, which is essentially G times M over R, where R is the distance scale of these two objects, but also a low velocity or non-relativistic limit. This is so because the Weyl theorem, at least for Newtonian gravity, locks these two objects averaged to each other, and that is why, in particular, this is a good approximation for quasi-circular bound orbits. Now, if you have very eccentric orbits, or even the limiting case of scattering, this is not a good approximation anymore. Velocities can become very large, and that's the domain of the post-Minkowskian expansion, where we're only assuming a weak gravitational field. And this is the domain we will be working in. This is the domain very closely connected to scattering amplitudes or to collider physics, where we just scatter two black holes with similar techniques like we would scatter two protons or so at the LHC. And then finally, there is the gravitational self-force expansion, which is a non-perturbative both in G and V, but perturbative in the mass ratio of the two objects. So you consider one very heavy compact object, which is encircled, or where a very light object is being scattered off. And that, of course, at leading order is nothing but the movement of a probe mass in a given space-time background. So if we're not looking at the spinning situation, it would be a Schwarzschild background. And at leading order, this is just the geodesic motion, which you can solve from within general relativity. And the self-force expansion would then be the first or the second correction to this geodesic motion. And that's a semi-analytic approach, because the way it is fleshed out at this point, there are also numerical aspects in order to do it. And here the state of the art is at the leading and partially sub-leading corrections to that expansion. You can also sort of see in this plot here on the right-hand side the general setup of these different expansion parameters. So down here we have the dimension of the separation, whether they're very close or far, the two black holes, the mass ratio, and in the z direction, the eccentricity. And as I said before, if they're far apart, then either Pn is good for the circular situation, Pm is good for the scattering situation. And if you have a high mass ratio, you sort of have an overlap with the self-force expansion, which also works for close objects. Numerical relativity, on the other hand, is good for very equal-sized and close black holes. So that's the general setup. So I'm going to focus on the post-Minkowskian, but I want to give you a flavor of the state of the art by contrasting the post-Minkowskian expansion versus the post-Newtonian expansion on the next slide. So here you have in green the various orders of the post-Newtonian expansion. Starting 0Pn is just Newton's gravity, and the first correction was done by Einstein, Infeld, and Hoffmann in 1938. Where you see the first correction in G, so you get a G over R correction, but you also get a correction essentially, from the relativistic setup by having a V squared term. And that sort of structure keeps on propagating. So the next order, you will go up to G cubed, but you will also pick up orders of V and so on. So at a given order in the PM expansion, you always go down in this direction, and it stops as soon as you hit the velocity-independent pieces. The PM expansion, on the other hand, is an expansion which is exact in V, so you always get the complete line up here, and the complexity here grows with the PM order. Complexity meaning the integration complexity of the underlying Feynman diagrams. And our group has now reached the 5 PM level, which is the present state of the art, which amounts to 4 loop computations. And the goal of this talk is to give you a little flavor of how that is being performed using worldline techniques. All right. So before I do so, let me now introduce the model, because we are going to use an effective field theory description of the black holes. First of all, the setup, when is that good? As I said, we have this separation of scales in the problem. So namely, we have the intrinsic sizes of the compact objects, which is of order of a Schwarzschild radius. So G times M or 2G times M is just an order of magnitude discussion. And then that has to be small with respect to the separation. So for the circular prop, for the bound state, it would be the distance R. For the scattering situation, it would be the impact parameter B. And that again is small compared to R, which is far out at asymptotic infinity where our detector sits. These are the separation of scales. And due to that, in particular, the first equality here, we can actually model the black hole or neutron star just as a massive point particle in GR. So that's the leading order contribution. So to an effective field theory description, a worldline description of a compact object. So the leading term is sort of blind to the question whether we're dealing with a black hole or a neutron star. You just have this massive point particle term. And then there's an infinite number of higher order, higher dimensional operators you add on the worldline, which capture the intrinsic degrees of freedom of a compact object. So one important aspect, of course, is the spin of these objects. So every black hole has a mass m and a spin, as I said before. And the systematics of this expansion is that we're going to work in our small parameter mg over b, and then it is. I mean, one aspect to note is that the spin of a black hole, its magnitude, is again limited by mgn. So it's of the same order as the expansion, or as the Schwarzschild radius. So from that, you can sort of set up a hierarchy of terms. So the first spin correction would be of the 1 pm order at pm squared order. You get a spin squared term, and the first non-spinning term, taking into account field redefinitions that you can perform on your metric, will be a term of order second derivative of the uh, the metric. So that's essentially a Riemann squared term, which is spin free. And this term here, for example, would be a term linear in the Riemann tensor coupled to two powers of the spin. So that's just the organization. I'm, for this talk, only going to focus mostly on the spinless case, but I just want to show you how we model spin in this worldline action, which is actually inspired by bosonic string theory, if you wish. In order to give the spin degrees of freedom to the worldline, we have to, next to the trajectory x mu of tau, also add an additional degree of freedom that captures the spin. And this we do by adding like a bosonic oscillator, so a d-dimensional complex vector field on the worldline A alpha mu of tau, which encodes the spin tensor or the spin vector by just contracting it with the Levi-Civita tensor and the velocity. So the theory we're looking at, the effective worldline description of a Kerr black hole or a neutron star, then looks as follows. It's given by this rather compact action on the worldline. We have just the spinless term. We have a kinetic degree of freedom, a kinetic term for the alphas, and then we have this first spin correction, which is of order. I mean, this is also a spin correction, but this is the spin squared term. The blue story is the story we would have for a Kerr black hole, and then a possible second operator you can write down is the red one here. And this operator really is the first to distinguish between a neutron star and a black hole, namely Kerr black hole has CE is equal to 0, whereas neutron star has a to be measured Wilson coefficient CE. And that's just the first of a whole series of these higher order corrections. But for most of this talk, I'm actually just gonna focus on this black contribution. Good. So it's an interesting and fascinating question what the effective field theory of a Kerr black hole is, because a Kerr black hole is unique once I give the mass and the spin, and that is understood to linear order in the curvature by an infinite series of higher order corrections involving the electric and the magnetic Riemann tensor, but it's still an open problem at higher powers of a curvature. But I'm not going to get into this much. All right. So how do we perform these computations? First of all, I would want to argue how you would do it sort of the traditional way. So let's switch off spin and go back to the initial action. I was jumping a bit. So this would be the square root form of the action. And before I showed you the Polyakov form, which are equivalent. But no matter what, we will have the point particle approximation here, and we have these two. We now take two of these objects, two of these point particles, and let them interact gravitationally. That means we just add a bulk gravity term and a gauge fixing term. And then the task would be to solve the equations of motion. So in the bulk you get, or from the metric, you get Einstein's equations, of course, and from the worldline, the geodesic equations. And being interested in the scattering problem, you can set up a perturbative scheme by saying, okay, at leading order, when I switch off gravity, these two objects would just fly on straight trajectories, and there would be no metric field. So that's the blue situation, straight line trajectories for the two black holes, and just the Minkowski metric. And then you systematically add, in a power expansion in Newton's constant, the corrections. So you will have deflections, and you will have the graviton-emitted radiation modes which appear. So you would take this ansatz and then go into this equation and order by order work your way up to, you would find the leading correction here, so H1, by just plugging in the straight line movement here, that would give you H1. You could then determine the X1 from this equation, and then you ping pong back and forth order by order to compute these corrections. Yet, what you would find is maybe more than you would want to know, because you will find the metric in all of space-time, although you're only interested in the asymptotic fall off of a metric, sort of the far field waveform, or you compute the exact trajectory, which is also not a quantity you would really be interested in. You would be rather interested in something like the change of momentum in the scattering process, because that determines the scattering angle, but also the emitted energy and the emitted momentum in gravitational waves, so the radiated energy in this process. So these are the observables you really want to focus on. And this approach that we developed, which we termed worldline quantum field theory, is something that directly lets you focus on these observable quantities. So in that sense, it's from the philosophy similar to the amplitudes program in scattering theory. All right, so WQ of t, how do we go about this problem? So here's again the problem. Going to a Polyakov form of this particle action, we get rid of a square root, so we just have a g x dot squared type of description of the black holes, in ignoring for now these higher dimensional operators, which interact through Einstein's gravity, as I said before. But what we're now doing is we're making a sort of a background field quantization of that problem. So we start with a solution to the three equations of motion. This is the black, this is the background. So two initial B's and two initial velocities. And then we take the deflection field, the blue deflection field Z, and the graviton field H mu nu as the quantities that we integrate out in a path integral. So we're going to do path integral quantization of this theory. It's a hybrid theory because we have the one-dimensional world line and a four-dimensional, or rather d-dimensional bulk. And we're going to compute one-point functions in this quantum field theory. But in the h bar to zero limit, and in the h bar to zero limit, the only quantities that survive are tree-level one-point functions. And it's like a fundamental theorem of QFT, which I don't have time to sort of review here, but it's rather straightforward to show that one-point functions computed in this manner of h and z at tree level solve the classical equations of motion. So you can use this Q of T machinery, in particular also Feynman diagrammatic expansions, to systematically set up a perturbation theory in G, in the PM expansion, to compute the metric field and also the deflection for the problem at hand. And the main advantage of this approach is that it allows you to import advanced quantum field theory technology that was developed for the collider problems in particle physics now to the realm of classical gravitational wave physics, and make quite some advances compared to the traditional approach. So I want to sort of show you, give you a glimpse on how these computations go. Good. So again, this is the theory we're dealing with. We have a world line and we have a bulk gravity theory. We do this, we were interested in a scattering scenario. So we have this background field expansion that I was showing to you on the previous slide. And we now have to look at first at the propagators. So we'll have propagators on the world line for the Zs, as these are just linear time derivatives appearing here, going to momentum, or rather energy space. You see that the two-point function for this theory here is just given by 1 over omega squared propagator. And it also goes like 1 over m being the mass of this compact object. So these are the propagators of the deflection modes on the world line. Then you also have, of course, propagators for the gravitons, that there's the need to add a gauge fixing. We do this in a generalized de Donda gauge. I'll get to that maybe later on. And that means if you plug this in, including the gauge condition, the quadratic term that you pick up gives you this propagator with a particular tensor structure here for the gravitons, and a 1 over k squared propagator very similar to a photon. The important and a little bit technical point here is that as we are interested in a dissipative problem, we should actually here employ the so-called Schwinger-Keldysh or in formalism to compute these things. The upshot of that analysis, I don't go through it here, the upshot of this analysis is rather simple. As long as we're interested in one-point function that's at tree level, which we are, the only impact of going through this analysis is that we are facing, or that we should consider retarded propagators in this endeavor. So we have a retarded graviton propagator and a retarded worldline propagator, reflecting the flow of causality in these diagrams that I'm about to show you. That, if you think about it, that does not come as a big surprise, because if you would have addressed this problem in the traditional way, say even by solving the equations of motion in a perturbative expansion using Green's functions techniques, as you know, we teach our students, say in electromagnetism, you should then also use retarded propagators in order to do that. And that approach sort of resurfaces here and makes a little distinction to the standard QFT analysis, where you have an in-out formalism in a scattering of elementary particles, where you know the in and the out state, and you want to compute the transition amplitude for that. Here, we do not know the out state. We only prepare the in state. That's the difference. Okay, so long story short, use retarded propagators. And then we also have to study the vertices. There are two types of vertices due to this hybrid character. We have vertices which reflect the interaction of the world line with the bulk. Now, as long as we're spinless, this is rather compact. There is only this interaction term, which means that we have a single graviton interacting with the world line. And plugging in this background field expansion, one sees that you will have just the graviton interacting just with the source, the non-fluctuating background, or it can also, you also have vertices involving one, two, or actually any number of deflection modes, simply due to the fact, I mean, naively, you would think there can only be two Z fields appearing here, but as H is to be evaluated on the world line, you actually, through, you know, if you expand it about this background field, you actually get higher Z interactions as well. So this is the story of the worldline vertices. Their structure is uniform, so they will always be proportional to the mass. Yeah, just coming from this coupling, they will be proportional to square root of G. That's due to the expressing the coupling to the graviton field. And they will preserve, and that's a very important point, they will only preserve one component of momentum, because it's sort of the projection of the it's the projection of the form momentum k of the graviton on the world line, so which is given by the form velocity here. And what you conserve is this component of k with the sum of all energies of this world line. And that's very important, because that's the reason why, although we're only computing tree-level one-point functions in this hybrid theory, we still have to do non-trivial loop integrals over the momentum, simply because at the vertices we don't have a full d-dimensional momentum conservation, but only one-dimensional momentum conservation for these worldline vertices. In the bulk, of course, we have full 4D momentum conservation, and in the bulk we have the standard graviton vertices, which you get by expanding out the Einstein-Hilbert action, which are highly involved structures. So and they come with any multiplicities. So the leading one is a 3 graviton guy, 4 graviton, 5 graviton, 6 graviton, and so on. The more legs you have, the more powers of square root of G you pick up, and they're all uniform second order in momentum. Now, the good thing is, of course, if you work at a given order in the G expansion, you only need a finite number of these vertices. And as we have pushed this expansion actually up to the order G to the 5, we actually now need at maximum the 6 graviton vertex, which is still a huge object. I mean, here we have optimized the analysis by adding going to refine gauges in order to minimize the number of terms in these vertices, but they are still huge. So you see that the 6th graviton vertex has more than 50,000 terms. So it's clear that these computations we're talking about cannot be done with pen and paper, but you have to do this with very elaborate computer algebra and software techniques. Good. So that's the setup, and that's the toolbox for which we do computations. You also do such a background field expansion in the presence of spin, where this is the action I showed you before, where we now expand about a constant background for the alphas and look at the deflections alpha prime. Now, due to the linear derivative here, you get a 1 over omega propagator, and this incoming value of alpha, if you wish, the alpha minus, encodes the initial spin of the objects we're looking at, right? So you have an initial spin, and then after the scattering, of course, the spin can have changed. And another observable that you will be, or we will be interested in, is the so-called spin kick. So how much did the spin change after the scattering process? Good. So that's sort of the setup. And now I want to show you how you can compute observables with this theory in the PM expansion. So
Sorry, Jan, can I actually ask you a question about the last comment you just made? The change in the spin, shouldn't this be will this be a fractional change?
Yeah, can be anything. I mean, we're talking about classical spins, right?
See.
So
Okay.
it's just the rotation of, it's just the angular momentum
Okay. All right.
of these objects, right?
Okay. All right.
Yeah.
Thanks.
Good. So here is the situation that we're interested in. We shoot in 2 black holes with velocities v1, v2, masses m1, m2, separated by this impact parameter b, and out come 2 black holes again under a scattering angle. So we're going to be interested in computing the scattering angle, sorry, as well as the radiated energy, which is carried away by the gravitational waves, and possibly also the recoil free momentum. So how, what is taken away on free momentum as well. So these are the observables if we're looking at the spinless case. And the object one that encodes all this is the impulse. So it's the change of form momentum of a given black hole, so like the first black hole before and after. So you compute the final momentum at tau is equal to plus infinity, and you subtract the initial one, which is just m times v 1 if I is 1. And then this, of course, you can also write as an integral over the acceleration. And then knowing that we have a background field expansion for x, that only speaks to the z fluctuation because the b plus v tau is just 0. And then if you go to momentum space, do a Fourier transform, you actually learn that this quantity is given by, as I said before, the 1-point function of z in momentum space in the limit when omega tends to 0, where you sort of cut off the final, you amputate the final propagator. So computing this 1-point function with in the limit of vanishing energy is cutting off the final propagator directly gives you the impulse. So delta P1 is diagrammatically at leading order in G, just given by this diagram here. You have one outgoing Z line, omega tends to 0. You exchange one graviton between black hole 1 and black hole 2. In these graphs, we always write these dots to sort of depict the background. So this is black hole 1 carrying mass 1 and velocity 1, and this is black hole 2 carrying mass 2 and velocity 2. At order g squared, you can exchange 2 gravitons, or you can see for the first time the graviton self interactions. So you have these 4 diagrams, and of course the complexity grows. G cubed, you have, this is a true loop problem. You can actually count the loops by sort of thinking of these inner dots as closed, and that gives you a counting of a loop. So this is a 3-level process. This is a 1-loop process. These are 2-loop processes. This is then 3 loops. And as I said, we recently finished with the 4-loop computation at order g to the 5. And that actually also was nicely published in Nature this year. And this is a problem which is huge, which, where we had some more than 420 diagrams to compute, which is really almost an industrial scale problem, for which we needed this large collaboration, because also the mathematics of these integrals becomes very intricate and makes contact to Calabi-Yau free folds. Good. So this is the impulse. You can also compute the waveform and the leading order diagrams. So here you're now interested in just a single graviton emission from the sum of all diagrams. So at leading order in the G expansion, you have these three diagrams which contribute. And this little movie I showed you at the very beginning of my talk is actually a visualization of a computation of these three diagrams. It's not a numerical simulation. It's the analytic computation we did, and you can nicely then just visualize these functions, and that's what I showed you. And then you can also compute the change in spin, the spin kick, what Gabriel just asked. And this is based on the change in alpha, in these alpha oscillators, and which you can assemble to compute the change in the spin tensor, or then translate it to a change in the spin vector. So that's the setup. So let me give you, in the remaining 20 minutes that I have or so, a flavor of this impulse calculation, because that's, as I said, where we went the furthest in the perturbative computation. So the workflow of this computation is very similar to what is being done in multi-loop computations in, say, QCD for collider physics. But there are certain changes that have to be done in order to adapt to the gravitational wave problem. So the first step is to generate the graphs, of course, and to find the integrand that you want to integrate. And this we do with a particular technique that I'll show you in a second. Then you reduce these to scalar integrals, which you then decompose in terms of master integrals through a particular technique known as integration by parts. And these master integrals are then integrated by yet another novel technique known as differential equations. So you solve high loop Feynman integrals by taking derivatives and setting up a linear differential equation, which actually teaches you what sort of functions emerge in the evaluations of these Feynman diagrams. And this is where the contact also to these Calabi-Yau free folds happens. And then finally, you have to still do, because you have a differential equation, you have to find the initial conditions. So these are called boundary conditions here, in which then gives you a complete answer. So I'll walk through this in some detail to give you a feeling of how that goes. The difference to, say, the collider physics story is that we're dealing with retarded propagators. So there are certain changes here that don't let everything go through very, very similar. So how do we generate the graphs? This is for this we use a Bern-Skeeler type recursion, namely because we're interested in tree-level diagrams. We can write down a Schwinger-Dyson type equation, say for the one-point function of z, which is sort of an exact expression which we can then perturbatively expand in G, and therefore just generate the integrand both for z and h. There's a similar expression for h, which is a bit more involved. So it just reflects all the possible couplings that you can have. And it's just in a sense, it's just a diagrammatical version of the geodesic equation and of Einstein's equations for the problem. And this we use in order to generate the integrand and get a structure of these diagrams. Now, there's another important thing that I only want to briefly mention here, namely that this computation which we're doing can sort of be filtrated with the self-force expansion. I told you at the very beginning that there's also an alternative expansion, not in G, but in the ratio of two masses, M1 and M2. And at leading order in the self-force, what you're facing is just the geodesic problem. So you have a very light black hole moving in the background of a heavy one. Now you can rediscover this actually in this diagrammatic expansion very nicely also through our diagrams, because what I want to do here now at the various PM levels, I want to just count the factors of M1 and M2 that appearing. And then that allows us to classify these diagrams in a very simple fashion. And that is due to the diagrammatic structure is very simple because every time a graviton touches a world line, okay, gives you a factor of m, simply because the worldline propagator goes like 1 over m, and every graviton worldline interaction is proportional to m. So that has this effect. So this diagram touches each side always once. So it's linear in m1 and linear in m2. And all these higher PM diagrams all only have a single touch on worldline 1, which means they're all linear in m1. So these are all how we call zero SF diagrams. And although, for example, this one down here amounts to a for-loop computation in worldline quantum field theory, which is not very trivial, the result is known because all this is captured by geodesic motion, just by GR, just by solving a geodesic motion in a Schwarzschild background. And then you can flip, M1 and M2. That means you just flip the sides of these diagrams, and that gives you this vertical here, which also extends down. So you see, although it's non-trivial from the computational point of view, from the QFT side, the first time you touch new ground compared to geodesic motion is at the two-loop order, at the 3 PM computation, which was first performed by the group of Zvi Bern and Radu Reuban in the US. And that's where you see the leading 1 SF contribution. And these are graphs where you would have, in this case, you would have an M1 squared and an M2 squared here. And this persists, so it goes down the loop order in this and in this direction. And you see similarly, and that's always every 2 PM steps you hit a new SF order. The first time a 2 SF graph appears, in this case here it will be M1 cubed, M2 cubed, is at the 5 PM order. And the situation is such, that's why the 5 PM computation is not complete yet. What we computed are all these terms down here with the exception of the 2SF. And that's something we're working on right now. So the results we have at this order are good if you have a large mass ratio. So that's all.
May I ask a question here? Sorry. Previously you mentioned a connection with Calabi-Yau's. At which loop order does this happen?
It happens here at the for loop for these contributions here and here. Yes.
Before loop.
The first time before you have at the free loop level, you see elliptic functions which can be related to a K3, so Calabi-Yau 2. All the other things are multiple polylogarithms that appear, and at the for loop order, you for the first time see these Calabi-Yau periods appear, pre-fold periods appear.
And if you were to go to 5 loop order or higher, would you expect an analogous structure to appear, to play a role? Is there a conjecture of the sort, or
not really? I mean,
really.
you could, but I wouldn't say that it's so simple. It's not clear at this point. We do understand what happens also at this level. So there are new Calabi-Yau geometries appearing here at the 2SF, but we haven't thought about the 5 loop. It has to do with the question of how you define transcendentality for these Calabi-Yau periods. So I don't think it's really clear. Okay, so again, looking at this 5 PM impulse, this is the structure that you're facing. If I just look at the mass dependence, and here you can see how it's sort of a problem decomposes. Of course, every mass sector is by itself gauge invariant, so they for themselves are well-defined quantities, and that's why you can focus in them. So we also computed the 0 SF diagrams more as a check of our algorithms, and then these are the 1 SF diagrams, which are non-trivial, and we're presently working on the 2 SF ones. There's also a way to define, I mean, I told you should always consider the retarded propagators, which gives you the full dissipative answer, namely that the sum of the 2 momentum changes, the 2 impulses, is not 0, but is equal to something, the 4 momentum that is radiated away, and that's exactly where these Calabi-Yau functions sit. You can also define a conservative subsector where you sort of switch off this effect, and this you can do technically by considering Feynman propagators here. But the real physics is, of course, the dissipative one. All right. Just to give you a flavor, I don't have so much more time, but the integral problem, I said the growing PM orders, the loop integral that you have to perform grow, and they are always of this structure. You have an overall um, 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 Fourier transform, and essentially, and then an n-1 dimensional loop integral, which has the following structure. You have, as scaling with the PM order, you have n-1 for every loop order. You have a single a one-dimensional delta function, which actually reflects the SF scaling, namely the number of V1s and V2s mirrors the powers of the masses that you have. Then the propagators are either graviton propagators or linear or iconal propagators, which come from the worldline. And then you have some numerator structure here. Importantly, these integrals that we're dealing with are still rather moderate with respect to what happens at high multiplicity or high loop processes in QCD or so, because our integrals are only depend on a single parameter, because there's only one dimensional quantity they cannot depend on. That's momentum transfer Q. So that Q dependence can just be scaled out by dimensional grounds. And the only parameter that remains is the relativistic gamma factor. So the product of V1 and V2. This because V1 squares to 1 and V2 squares to 1. So there is no scale involved with that. And that's why everything depends on gamma. And that we then translate to a dependence on X. So all our integrals just depend on X. And when you do Pn, you would expand exactly in this factor here. And then there's a standard way, Passarino-Feldman, to reduce the numerator structures, I mean, with tensor integrals to scalar integrals. Let me not get into that, but let me just give you a flavor of how these integrals look that we're dealing with. You can actually read them, as I told you before, really as normal loop integrals. And the dotted lines inside then correspond to cut worldline propagators. So again, the bulk propagators are just 1 over k squared. You have these k dot v iconal type propagators, and the ones on the dotted world lines translate once you integrate out the energies of the world lines of the world line theory. You land on these delta functions effectively. So an example would be this integral here, which you can directly translate to a loop integral over L. You have these two propagators, L squared, Q minus L squared. So L runs in. So this is the direction of L. L runs down here and Q runs up. And then you have a delta L dot V2. This is this thing here. And this is the top propagator, the worldline propagator. And you have this outgoing line. Also here, note that the direction of the causality flow is always manifest from these diagrams. It's always fixed, and that gives you the direction of these retarded propagators. And all these integrals just depend on this gamma factor, as I said before. All right, and we can even conjecture an all-loop integral family that will capture any order of the SF expansion. We did so, which is at least true up to the 5 PM order, which can be written rather compactly. And these are already the animals that give rise to these very nice mathematical structures. All right, so how does one now perform this? The key idea is, if you have you identified this integral family, you expressed your whole integrand as a huge sum of actually millions of these scalar integrals, which all fit into a single integral family, which I sort of sketched before. And the thing to do now is, or the way to address it, you can think of all these members in this integral family as living in some high dimensional vector space, but that is finite dimensional, although you have millions of these integrals, but it's spanned by a actually 230 times plus 230 dimensional basis. There's a factorization by parity of these integrals. And what you want to do is you want to express any representative, any scalar integral in this integral family as through this basis of master integrals. And this basis you find through a procedure known as integration by parts. So you just write down an exact identity where you take a total derivative of your Feynman integral family, and then you set up linear equations that can be solved and reduce any expression you have to master integrals. So this is a well-established and highly developed strategy in multi-loop Feynman diagram computations. And for us, it was very, very crucial to have Johan Uzovic on our team, who is the author of Kira, which is one of the leading tools to do that. And even prior to publishing this 3.0 version, we could use it in order to really crack the problem. So we had to reduce 10 to the 6, so millions of scalar integrals to this basis. And this actually also was quite computer intensive on high performance computing. So this is where this is really the bottleneck of these computations. And that then allows you to study these master integrals. So now you have to solve 230 plus 230 master integrals, and that you do by yet another technique known as differential equations. So I told you before, these master integrals just depend on a single parameter, in this case x, and of course on the dimensional regulator. And they obey a linear differential equation, because if I take a member of that family, I take a derivative with respect to x, it will stay in that family, and I can then decompose it again in the basis I have, so I can express it as a linear combinations of the masters. So that gives you a linear differential equation with a particular, large dimensional matrix M. And what you then seek is a similarity transformation such that this matrix, this differential equation transforms into something where the epsilon dependence on the matrix factorizes. And once you have that, you can straightforwardly solve this differential equation in a power expansion epsilon, which is what you're interested in, because at the end of the day, you're only interested in the first few terms in the epsilon expansion. You actually need the epsilon because individual Feynman integrals are divergent. You have high power of epsilon poles, which all cancel in the final result, and you get a finite result. And the structure of these matrices that appear in the differential equation tells you what sort of mathematical functions appear in your answer. And here are the heat plots of these two matrices, the even and the odd parity matrices, which we had to deal with and then solve. And the color coding is such, if I go to the second one, the color coding is such that you can identify the types of functions appearing. So everything on this, and it's actually dictated by the diagonal. So everything here in this blue will give rise to multiple polylogarithms, and the purple stuff will give rise to elliptic integrals, and the red, this is exactly the sector where the Calabi-Yau threefolds sit. So that's sort of what I said in words. These are the function spaces that appear, multiple polylogarithms, which are just iterated integrals with kernels given by 1 over t minus AIs. One speaks of the alphabet for these AIs. So you have, depending on the loop order, you have more and more iterations of that, and that gives you higher and higher polylogarithms. These are standard functions which appear in Feynman diagrams. We also see the emergence of elliptic integrals of the first and second kind, and then here for the first time these Calabi-Yau threefold periods, which arise as by integrating this holomorphic freeform on natural cycles for these Calabi-Yau free geometries. And this is exactly where we needed the input of Albrecht and Christoph in order to be able to deal with that. So here's again this heat plot, and this is maybe the most exciting part of it. This is this Calabi-Yau threefold. You can also relate it to a particular integral. And what you see is you can translate the problem of solving the differential equation in that sector to solving this fourth order differential equation in Z. Z is x to the 4. And the periods appear exactly here. They solve these differential equations, and they're also related to a particular manifold that's defined by this relation. The elliptic integrals are related to a particular K3s, which sit in these entries here. So the important thing is that you can do that, you can solve it, and then you need to still solve the boundary conditions, but maybe let me not get into this. This is a bit technical. And at the end of the day, you can then assemble everything and get, for example, the scattering angle. So here I show you just to give you a flavor of the results, the scattering angle for the scattering process in the center of mass frame. There's a certain subtlety how you define it exactly in the presence of recoil, because the initial and the final center of mass are not the same. But let me not get into this, just to give you a flavor. So this is the scattering angle normalized by essentially the energy over the total mass. This is the gamma. So this is the 1 p.m. result, which is a very simple back of the envelope computation. This is the 2 p.m. result. These, as I said, just follow from geodesic motion. So you can already read them off from geodesic motion. And this is the 3 p.m. result, where for the first time dissipative effects make an appearance. And the 1SF contribution, which is denoted down here, this you only get right if you really use retarded propagators. And you can see the SF expansion by the, it's a little bit hidden, but it's related to this new parameter, which relates to these quantities here. I mean, M1, M2 over M1 plus M2 squared. Good. 3 p.m. At 4 p.m. for the first time, you see these elliptics, as I told you. You always get squares of them, and that's why they're related to this K3. The squares are necessary because there's a symmetry in x. X goes to 1 over x in the problem, and that's why a single elliptic integral could never appear. You always have to have quadratic ones. And then there's polar log contributions. And at the 5 p.m. order, this is what we computed. For the scattering angle, as a matter of fact, no Calabi-Yaos appear, and also no elliptics. Everything is expressed in terms of multiple polylogarithms. And we have not, I mean, as I said before, we're still missing this 2SF piece in the final result. So it's one interesting question whether the Calabi-Yaos will appear there as well. They do appear in the radiated energy. And here's just to stress that we have full analytic control. Here's just a snapshot of this part of this scattering angle at fifth order. You can see everywhere these multiple polylogarithms appearing, and they're always dressed with polynomials in gamma. So this is the structure of these results. Now, an important question before I close is, of course, how does it compare to reality? Now, so far, there haven't been detections of scattering events, always of bound state mergers, but we can compare to numerical relativity simulations, which solve the problem on supercomputers. And these are these black dots here. So we here studying, or I'm plotting the final scattering angle as a function of the impact parameter in units of the Schwarzschild radius. And of course, the perturbative regime is one where the impact parameter is large, right? Large with respect to GM. And there you see, so here you see 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m. That's our computation. And that, of course, gets better and better the further out in the perturbative regime you are. But you also see that when this becomes smaller, that you start differing. However, in this perturbative regime, we're better, if you wish, than the numerical relativity error if we just estimate our error as the difference between g to the 5 and g to the 4. This is also a scattering of equal masses, because for the numerical relativists, simulating unequal masses is very complicated at 50% of the speed of light, so it's rather fast. And this can also be compared to self-force computations, which also looked at the problem, and they sort of with numerical approaches, and they confirm our results, which is a little bit hard to read off here, but this actually confirms our results. You can do even better by doing resummations in this problem. This is known as the effective one-body model. So that's a little bit of a phenomenological model, but it sort of combines the fact that you know the geodesic motion, and you know. So what you do is you write down an effective one-body description with certain perturbation parameters, which you fix from the scattering, and then you use that to extrapolate it beyond the scattering regime. And if you do that with the results that we have here, only used up to 4 p.m., you see an enormous increase in the predictability. Here are again the naked perturbative results, and this is their resummation. And you see at the 4 p.m., one is already very, very close to or almost on top of these numerical relativity predictions for the scattering angle in the scattering problem. Good. I think my time is up. I should close. Just give you an overview. So this is, of course, an area where many groups are working. I focused on our approach. There are other approaches involving scattering amplitudes, which have also made important contributions. And there's a whole sort of race for higher PM results, both in the spinless case, which I focused on, or including spin. So this is sort of the map of all these contributions. And you can see that if you're interested in the full 5 p.m., there is sort of a counting with the PM expansion and the spin expansion. And what we're striving at is to have precision at 5 p.m. At all orders in the relevant spins. And that's this red line here. Good. So let me close. I won't talk about the gravitational waveform. There's no time. I'll just show you another nice simulation for computing the waveform. The first one I showed you was the cross polarization, and here now I show you the plus polarization of the gravitational wave in this scattering event. Or maybe I showed you this already, I'm not sure. Another interesting thing is the memory effect. Namely, if you look at the metric at infinity before the scattering, it's completely flat. The scattering happens, the gravitational wave passes through, and if you have two freely floating masses, they sort of shake. And after the wave went through, they are not at the same distance as we were before. So there's a memory of what happened, and we can actually plot the metric now over the two angles of a celestial sphere. And you see after it went through, there's sort of a distortion in it. And this is for the plus polarization. So you also have a very nice structure. All right. I think that's what I wanted to tell you. Before I close, I just want to stress that I think this is a very, very fascinating area of research, because it sort of brings together, many aspects of physics and mathematics to a problem which is of real, also observational interest. Techniques from collider physics, state-of-the-art Feynman integration technology, differential equations, integrations by parts are necessary. Insight from classical gravity, the geodesics or the resummation techniques are important. Advanced algebraic geometry, Calabi-Yau threefold periods are needed to express these results, and even inspirations from string theory. For example, the way we model the spin degrees of freedom is something that is inspired from the point particle limit of strings. So that's what I wanted to tell you. Maybe I'll skip the outlook and just want to thank my great team. Without that, would have not been possible. And yeah, I'm happy to take questions.
Thanks very much, Jan, for this very nice talk. Thank you. So, question.